Okay, now I try to give you a mathematical interpretation about the meaning of the core meaning of the frog measurement. Say we have a power spectrum, but it can correspond to arbitrary spectral phase, right? There is no limit about your spectral phase. So essentially, it is impossible to uniquely determine the spectral phase from your power spectrum. Correct? Okay? So it's the failure of one-dimensional phase retrieval problems. This is a single variable problem, right? You have power spectrum, single variable. It's not possible to get the corresponding spectral phase uniquely. It's also a one-dimensional function, right? It must be failed. Okay. But things are very different if you move from one dimension to two dimensions. Okay. This is a simple fact. If you can record a two-dimensional trace A sub sig, we have seen this many times. It's just gated signal, right? Signal A of t times gate G of t minus tau. This is gated signal. But it's not a 1D function, it's a 2D function. You have two variables, t and tau. If you can record this, actually you can uniquely determine the signal A of t by a simple integral. Okay, let me show you. Just the integration with respect to another variable, tau. And the integrand A sub c is replaced by A of t times G of t minus tau. But integration is performed with respect to variable tau, so A of t is just a constant, can be extracted out of the integration. And the remaining term can be integrated. But no matter what is the result, it's just a constant, right? So after the integration, you got some constant times A of t. So you got the shape of A of t already, right? So you just need a one-dimensional integration. You can recover A of t, at least the shape, uniquely, without ambiguity. Okay? Any question? So in terms of pulse measurement, if you want to know the shape of A of t, it seems that all we need to do is to record this, A sub sig. But this is still not frog, right? What did we record in frog? Not this, but the power spectrum of this one. Okay? 所以我们其实没有直接量出它哦，我量到它我就简单了就积分就结束。我没有量它，我只有量它的 power spectrum。但是事情有没有救？还是有救啊？我们再往下看。Here I assume the Fourier transform of A sub sig, but remember you have two variables t and tau. Here the Fourier transform is carried out with respect to another variable, tau. So after that, you got a spectrum denoted by big A tilde sub sig. And the variable t remains. Variable small tau after Fourier transform becoming variable big omega in our definition. So tau and the big omega are Fourier transform variable pair, just like t and the small omega. Okay? So this is the definition. The gated signal spectrum in the delay frequency domain is A sub sig tilde. Okay? In other words, the gated signal in the time domain can be written as inverse Fourier transform of big A sub sig tilde with respect to the variable big omega. It's just equal representation. Okay. Then what is the Flock trace? By definition, it's this, right? We have seen this many times. The Fourier transform of A sub sig, but with respect to variable small t, and the taking absolute square. That is the representation of Flock trace, right? But if you replace the green one, small a sub sig, by this definition, the inverse Fourier transform representation, you got this. So what's this? Your Flock trace is actually the absolute square of a double Fourier transform of a two-variable function, big A, tilde, correct? This is a two-dimensional function. You have two variables. And the Fourier transform can be performed not just with one variable, but two variables, right? 所以这个就是二维的傅立叶转换之后取绝对值平方嘛，这就是我的 Flock trace. Okay? So in other words, Flock trace is actually the two-dimensional power spectrum of big A sub sig tilde. Is it okay? 二维函数的 power spectrum 是什么？做了二维傅立叶转换后取绝对值平方，才叫它的 power spectrum。现在不是一维，是二维。OK？ 那我们这个简单的推导就告诉我，我这个新定义的函数，把它做二维傅立叶转换，再取绝对值平方，就是我的 Flock trace. So what do we actually measure? The power spectrum of the red one, A sub sig tilde. Now it's a matter of two-dimensional phase retrieval problem, right? If you have power spectrum, can you get the phase uniquely? If you can, you got the red one. Equivalently, you got the green one, small a sub sig. And if you got the green one, small a sub sig, you can uniquely determine A of t, the target, by a simple integration, as shown in the previous slide, right? So the problem is solved. Okay, so retrieving small a sub sig, actually it's equivalent to retrieving A of t, our original goal, signal field. From Flock trace is equivalent to a two-dimensional phase retrieval problem, or retrieving the two-dimensional phase of big A sub sig tilde from its power spectrum. 有 power spectrum, 我可不可以抓出 phase? 问题本质是这个样子。我们知道一维已经不可能，你只知道一维的 power spectrum， 你绝对不可能唯一的决定一维的 phase。那现在问题是我已经把它推进到二维了，有没有可能？对不对？如果还是不可能，那我这个 interpretation 也只是再次告诉你 ，it's impossible. But people in diffraction optics and other fields have known this two-dimensional phase retrieval problem for many years. There is solution. 很早就知道这个是有 solution 的，那也就代表我的 pose 是有机会解出来的。Okay. Now I just show you the very basic algorithm for data reversal, the so-called iterative Fourier transform algorithm. Okay. So there is a loop. So you have to repeat many times. Okay. Initially, you have no idea about the signal field, A of t. So just give a random guess. Usually it's a random field. Okay. This is your starting A of t. Then you can use the gate constraint. What is gate constraint? It means it depends on your setup. For example, if you perform SHG Flock, then the gate pulse is equal to the signal pulse, G equals A. Okay? Then, if you have A, you must be able to determine G. uniquely, right? Of course, initially, the random gates of A of t is wrong, so you will get a wrong gate G as well. But it doesn't matter, it's just step 1 only, the first loop only, right? But if you perform other Frog measurement, G is related to A in different relation. For example, in polarization gating Frog, G equal to A absolute square, not equal to A. But in that case, if you know A of t, you can uniquely determine G of t as well. So once your setup is fixed, the relation between A and G is fixed as well. This is so-called gate constraint. Okay. Then, if you know A and G, you can multiply them together at different sampling time tau. You got A sub sig, the gated signal. Just the product between A of t and G of t minus tau. Okay. Any question to this point? 应该没问题吧？我的开始我当然不知道 A 是什么，随便猜没关系。你只要有 A， 即使是错的，你也可以推出 G， 因为我硬体上已经决定 A 跟 G 的关系。那接着就把它相乘，得到一个2维的 gated signal， 这里都完全没问题，对不对 ？Okay, now we have to jump to the frequency domain. So performing Fourier transform with respect to a variable t, you got big A sub sig. Or remember, this is different from A sub sig tilde in the previous page, okay? Because here we perform Fourier transform with respect to small t. 上一页 A sub sig tilde， 我要加一个 tilde 的原因就是不一样。好，它是什么 ？big omega。好，所以不要弄混。这里我不需要做2维傅立叶转换，我1维转换就好了。OK。So this is just the complex spectrum of the gated signal, right? Then we can perform the data constraint. What is data constraint? Your experimental data, which is Frog trace, right? And mathematically, we know the Frog trace must be the absolute square of this one. The power spectrum of your gated signal is defined as the Frog trace, right? So your data must tell you the correct absolute square of this. But the data does not tell you the phase of this one. Okay? So what can you do? You just replace the magnitude of big A sub sig by the square root of your Frog trace, while leaving your phase term intact. Okay? Because we have no clue or information about the phase. So just leave it alone. This is the data constraint. So this is the modified gated signal spectrum up to this point. Then performing inverse Fourier transform back to the time domain, you got updated or modified gated signal in the time domain. Then according to our previous analysis, you just need one-dimensional integration with respect to delayed tau. You should get A of t. So this is the updated A of t in the first loop. Okay. Then just keep on going, many loops. And eventually we are expected to converge to the right electric field A of t. Any questions?
In what cases it will converge?
Oh, okay, that's the next line. So during the iteration, you have to examine how good is the current A of t is. If it is good enough, we stop the loop, right? We cannot do it infinitely. But how to numerically or quantitatively evaluate the quality of your solution. This is what you need. The frog error parameter, G parameter, which is defined here. Look at the difference term. I frog super n means the calculated frog trace at the nth loop. So this term will change with number of loops. And the I frog is fixed one, the measured frog trace. So you compare the calculated frog trace with the measured frog trace and evaluating the difference point by points. Okay? Then normalize to the number of total points. Taking a square root, you got some number. If the number is smaller, that means these two are closer with each other, right? 这两个越像，这个计算一定会得到一个越小的数字。所以你就 monitor 这个数字有没有一直变小。如果呢，它不再变小了 ，even going through more and more loops, the G number does not decrease anymore. You can stop the loop. Okay. So that's the entire algorithm, iterative Fourier transform algorithm. Any question? Okay, I think the idea is not difficult, at least easier than the previous analysis about the two-dimensional phase retrieval problem. 所以你即使不了解那个二维的 phase retrieval problem， 你也可以直接看这个图，就该了解怎么去 implement 这个 algorithm， 算出你的 electric field. Okay. Some practical issues. To properly evaluate the G number, it is essential to normalize your frog trace to unit peak in each iteration. Okay. What does that mean? If you have, for example, your calculated frog trace is exactly the same as your measured frog trace, but you have a proportional constant like 10, then what's the number after calculation? You got a big number. And it's unfair, right? It's only the shape mattering. So you have to normalize your calculated frog trace, for example, to unit peak, same as this one. Then the number, the G number, would be a fair evaluation about the difference between calculated and measured frog traces. That is the point. Secondly, A of t and a shifted version of A of t will produce the same frog trace. That means frog trace is insensitive to absolute timing. It's clear. It's only sensitive to relative timing. Okay? So if you do nothing, your calculated A of t tends to drift during iteration. The A of t 会跑来跑去。Okay? 所以呢 usually you have to lock the peak of A of t at, for example, t equals 0. 你刻意把它锁下来，要不然它会一直跑来跑去。This is more serious. Okay? Convergence of iteration only means there is some A of t corresponding to a similar frog trace as you measured, while the uniqueness is not guaranteed. Okay? It's still possible. You have a different pose A of t, but corresponding to the same frog trace. So you got some solution, but not guaranteed. It's a unique solution. That's the weak point of frog measurement, because it relies on iterative algorithm. So it's not analytic solution, right? Uniqueness could be an issue. Okay. This is also practical. Temporal and the spectral resolutions, I use symbols dt and d omega to denote temporal resolution and the spectral resolution. They are determined by the omega and the delay window sizes of Flock trace. Okay, what does this mean? The time resolution of your electric field, A of t, depends on omega window size, while your frequency resolution depends on the delay window size in your measurement. Okay? So Flock trace has to be an island surrounded by sea of zeros, like this one, the right one. This is a good Flock trace. The white color means data 0. Okay? This is an improperly sampled Flock trace because you can see in one axis it's cut. The signal does not decay to 0 while your scanning terminate. For example, this is if the horizontal axis is delay axis, it means your delay scanning window is not big enough. Then what's the price you have to pay if you go on using this Flock trace? Your delay window size is too narrow. That will give a worse spectral resolution after your data reconstruction. 你解出来的 pulse 在 frequency domain 的解析度会太差啊！如果你停在这里。So it's important when you take Flock traces, you have to make sure it's an island surrounded by zeros. Some Flock varieties. Okay, SHG Flock is not the only choice. Here I show you some alternatives. Like cross correlation Flock. You can synchronize the reference pulse B of t as gate instead of using the signal pulse A of t itself as gate. Then you can have cross correlation Flock or X Flock if the gate pulse B of t is known in advance. For example, you perform some Flock measurement to characterize B of t in advance. Then you send the reference pulse crossing with the signal pulse, okay? And inside the crystal, many different nonlinear interactions can take place. For example, the red dashed paths indicate the optical parametric amplification process, okay? So you can recode the OPA spectrum as a function of delay. You got OPA Flock. Or another path, ground path, indicates the DFG, difference frequency generation process. You can recall the spectrum, you got DFG Flock, okay? And if it is OPA Flock, the gate is related to your reference B of t in this way. G of t is not equal to B of t. It's equal to cosh of B of t absolute value times G times L. G times L is a constant. Okay. But in any case, you have to figure out what is the shape of cosh function. But in any case, G of t is a narrower shape compared with the input B of t. Okay. This is just another gate pulse. Okay. Then, if you do so, you can measure the OPA Flock trace. After data iterative algorithm, you can get a trace like this, which look similar with each other, right? And you can have the signal pulse in the time domain or in the frequency domain after iterative algorithm. And the key point is OPA gain can be very large, 10 to the fifths in this case. Okay? So it means your signal pulse, the red one, can be very weak. You just use a strong reference pulse, providing strong gain such that your OPA spectrum, power spectrum, is still has sufficiently good signal-to-noise ratio. Then the measurement succeeds. Okay. In this case, the signal pulse can be as weak as 50 attojoule per pulse. Okay. and you can still reconstruct the electric field accurately. And even surprising, if B of t is unknown, your reference is also unknown, it's still possible you can retrieve both A of t and B of t simultaneously. This is so-called blind frog. Okay. So you have cross-correlation frog, you have blind frog. Why is it possible? Why can we obtain both A of t and B of t simultaneously? It's still due to the data redundancy, right? N squared is still much larger than 4n. Not just 2n, 4n. It's still much larger than that. So data redundancy remains. You can have them both. The last one is about single-shot frog. We talk about single-shot intensity autocorrelation, and it's also possible to do frog with single shot. This is so-called the Bernoulli technology. It looks complicated, but actually it's just the French of frog. Okay, 法文里面的青蛙. So how do they do that? This is the original SH frog setup. You need a microsensor interferometer to get 2-pulse replicas. You need a thin crystal and a spectrometer to measure the power spectrum for each delay, right? But it's too complicated. They can replace the microsensor interferometer by a Fresnel biprism. Do you know what is Fresnel biprism? 立体图大概也知道嘛，就是一个棱镜柱，所以它会怎么样？让你一道平行光进来，出来变成 crossing beam. Okay, why do we need crossing beams? Remember the single shot intensity autocorrelation. We need 2 crossing beams such that different lateral positions correspond to different delays, right? So this is for that purpose. So without the microsensor interferometer, a single biprism gives you different delays along different lateral position, maybe x direction. Okay. But we need spectrometer in principle. It turns out that they just replace the thin crystal with a thick crystal. With a thick crystal, that means different colors will be phase matched along different output angles. So angular resolution is there. You do not need a spectrometer, right? Spectrometer is used such that different colors propagate along different directions. Now you can use the thick crystal and the phase matching mechanism to implement the same function. Okay. So say the angular dispersion is along the y-axis, delay is along x-axis, then you just need a 2-dimensional camera to capture the data. You can get the frog trace in one shot. Okay, you do not need delay scanning. Okay. And this is the experimental result. With standard frog trace, you got this one interaction, you got this one. With Bernoulli, the simplified apparatus, you got the measured trace, retrieved trace. So they look very similar. And they get essentially the same time domain waveform and the frequency domain spectrum. Okay, so this is a very genius design of a single shot frog measurement. Okay, any question? No? Okay, so let's stop here. See you next week.